Okay, here is a perfect scenario for the shell method. So I want to have R be the region bounded by this function, f of x is equal to sine x squared, the x-axis, and the vertical line, x is equal to the square root of pi over 2. And I want to find the volume about the y-axis. So if I were using the disk method, that means if I'm going around the y-axis, then my function would have to be in terms of y. Is there any way for me to solve that to get that f of x is equal to sine x squared to be in terms of y? No, that'd be nutso, right? So because I'm going about the y-axis and my function is in terms of x, right? That's the whole point. The point is, if I'm looking at this function, it is in terms of x, so I need my dx as my differential, but I'm going around the y-axis. Boom, we have shells. So my volume here is going to be my integral, and I'm going from right here at 0 to the square root of pi over 2. And then I've got 2 pi RH. So you've got 2 pi. Because my differential is dx, my radius also has to be in terms of x because that's the value we're talking about. And then I've got my top function here, which is sine x squared, minus my bottom function, which is the x-axis. That's where that 0 comes in. Y equals sine x squared minus y equals 0. All right? Okay, now you just clean it up and do business. So volume, I'm going to throw that 2 pi in front. Again, it's a number, so I'm not going to mess with that. The square root of pi over x, pi over 2. And then it's x sine x squared dx. Now, let's do a little U sub. And remember, we are in Calc 1, so they set our problems up for us super nice. Thank you. I love it when that plan comes together. So anytime we do a U sub, we're always looking for that inside part, right? That crazy part. That's what we want to go for. So x squared does the trick. And the other beauty of this is I now have 2x dx. Boom, x dx. So I'm going to throw that 1/2 in front because I divide both sides by 2. And let's rewrite it. I'll go back to red even though it's my least favorite. So I've got 2 pi divided by 2 out front. I'm going to get the bounds here in just a second. And I've got now sine of u du because everything else works out. Okay, so at x is equal to the square root of pi over 2. Oh, lo and behold, if you square a square root, you just get pi over 2. Oh, well, didn't that work out nice? At x is equal to 0, u is also equal to 0. Once you commit to the u, keep moving forward with it. Why in the world would you ever go back to x on some mess like this? You wouldn't. That's why we are not going to. Scoot this up a little bit. Oops. Those 2's obviously cancel out. So the antiderivative here of sine is going to be a negative cosine. So I'm going to put that negative in front of the pi. And I've got cosine of u from 0 to pi over 2. Now I'll leave that negative pi in front because I don't really want to mess with it. So negative pi, and I've got the cosine of pi over 2 minus the cosine of 0. What's the cosine of pi over 2? 0. What's the cosine of 0? 1. So a negative times a negative is just going to be a pi. Sweet, right? Yeah, it is. Nice. Okay, let's do another example. I didn't get this one written out in advance, so we'll write it out right now. Okay, here's example 2. We're going to let R be the region in the first quadrant bounded by the graph that says region N. Those are actually two words, even though it didn't look like it. Bounded by the graph, y is equal to the square root of x minus 2 and the line y equals 2. We want to find the volume of the solid. And it's generated about the x-axis. Nice. Nice. Okay. Let's do this thing. So we've got y is equal to the square root here of x minus 2 if we're going to graph this out. And it's in the first quadrant bounded by y equals 2. All right, so there's y equals 2. If I've got this, so I know this is a line. Y equals 2 is going out there. And I've got here the square root of x minus 2. Now remember, back with your algebra skills, transformations of a graph. I know that the regular square root function graph goes like something more like this. So if I'm looking at that, I have this x minus 2. Remember, anything on the inside of transformations is opposite of what you think it will be. So I'm actually coming over here to, and then I can do my regular square root graph. So I've got a point here, and then it would be 1. And then a point right here. Right? And it goes up from there. All right? Okay then. So then that's my square root function. And you could plug these in to see. Oh, if I plug a 2 in, 2 minus 2 is 0. If I plug a 3 in, 3 minus 1 is 1. If I plug in a 2, 3, 4, 5, 6 right here, 6 minus 2 is 4. So the square root of 4 is 2, right? So it all plays out. Here is my region. All right. Now, if I'm trying to look at this region, I have, if I wanted to do this, even though about the x-axis, this is swinging me around the x-axis, right? So even if I wanted to look at this x-axis that we have, I'm trying to come up this way. Well, this function is different than this one, and I can't do that. I can't have two separate bottom to top functions. However, if I'm coming this way, I'm going to make this blue. If I'm coming up here this way and hitting my graph, right, I can make this cylinder sitting on that axis. Ah, cool, right? Yes, it is. So now I've got this cylinder. If this cylinder, I'm going around the x-axis, and my cylinder is sitting on the y-axis. Sitting on the y-axis, meaning that I have a differential of dy. And we can do the exact same thing. 2 pi r. I'm sitting on that axis. If I'm sitting on that axis, then what is my differential going to be? Dy. Exact same setup, so let's go with it. If I have this function right here, let's go black on it. This function is y is equal to the square root here of x minus 2. I've got to get that over here to be in terms of y. So you square both sides, add 2. Oops, y squared plus 2 is equal to x. And now I have my function in terms of y. All right? Okay, so volume here is going to go from C to D of 2 pi. My r is now a y. And then I'm going to write f of y dy, just so you can see what this is. Still 2 pi r h. and this is going to be my height going forward, and then this is going to be my radius, which is that y value. Okay, let's do it up right now. I'm going to scoot this up a little bit. I'm sitting on the y-axis. Everything is in terms of y, including my bounds. So from 0 to 2, 2 pi, r, which is y in this instance, and then the height is going to be my function, which is y squared plus 2 minus 0, because it's on that axis, right? dy. So it doesn't matter. You literally solve it the exact same way. Whichever axis you are sitting on, that's where all your variables, all of your terms need to be in that. So I've got 2 pi. I'm going to throw that out here from 0 to 2. And I've got y cubed plus 2y dy. And then integrate. It's just as easy as that. I've got 2 pi, and I'm going to have a 1/4 y to the 4th plus a 2 over 2. I'm not going to write 2 over 2. I almost did, but we're better than that. Y squared from 0 to 2. Now plug it in. 2 pi, and I've got 1/4 2 to the 4th plus 2 squared minus 0. Because 0 plus 0 is still 0. Now here's the beauty of this when you've got all these 2's in here. 2 of those 2's take out 2 of those, right? Nice, right? Yeah, it is. And that number sense really pays off. And I've got 4 plus 4, which is 8. So my volume here is 16 pi. Whichever axis you are sitting on, that is where all of your variables are in terms of that axis, right? Nice. So sometimes it's easy, I'm going to squeeze this in, to manipulate and come back to this and manipulate it to be in terms of y, because I'm sitting on this y-axis. And I have to go this way because here I've got 2 separate functions I'm looking at. I can't do that. It all has to go from my base of my cylinder up. Even with the other functions, I'm not just finding area, I'm finding this whole volume. So it's like this U-looking bowl with a real thick bottom, right, that I'm making. Okay, good. We